Hello dear students. Today we will be discussing about high resistance measurement using a technique which is known as method. So first we will look at what are the different issues that is associated with measurement of high resistance. So once we are planning to measure a high resistance value which is in the range of mega ohm range or mega ohm values, the currents that are associated with the measurement will be very low. So you have to use highly sensitive instruments to measure such currents. Now you have another issue which is known as the surface leakage current. Okay, it can be due to the different impurities that are associated. It can also be due to the impurities that are within the this insulation also. So we are generally measuring high resistance for insulators or insulation. So in case of insulation, if you have some impurities within present within the insulator, such impurities can result in leakage currents. So if you have an insulator of this manner, if you have so your conductor is at the center, suppose. So this is your conductor and this part is your insulation. So the purpose of insulation is to prevent any current that is flowing through the core or through the center of the part, this particular arrangement or the conductor, to reach the surface of the cable. So the insulation prevents the charges from reaching the surface. But if you have any impurities present in the insulator or within the insulating material, you can have some leakage currents flowing within these insulators. These impurities can be in the form of dust particles that enter within the insulator during the manufacturing process, or some air bubbles which affects the total insulation properties. So such leakage currents can affect the overall performance. So once you are planning to measure the resistance of the insulator, such leakage currents will provide alternate paths for the currents to flow, so that the total current measured will be sum of the currents which are passing through the desired path plus the leakage currents. So such currents has to be reduced or it has to be eliminated in order to get the accurate value of the resistance that is being measured. So here this can be eliminated using guard circuits. Okay, so we'll discuss about guard circuits in the head. The resistance measurement is also affected by the temperature, humidity, as well as the voltage that is being applied. If there is any inaccuracies within such regions, such elements also. Again, you have electrostatic effects. You will be having stray charges introduced in the measuring circuits, because since the current levels are very low, as I've already told you, you'll be using higher voltages in order to increase the current levels. So once you are having higher voltages, so these higher voltages will be inducing some stray charges in the measuring circuits. So these stray charges constitute some currents which can be entering the measuring values or adding up with the measuring values, which introduces some errors. And this charging current is due to the capacitance of the test object. So once you switch on the supply, during that process you will be having some transient currents flowing in the system, in this measuring circuit. So such transient currents, which you have already learned in your circuits portions, so such transient currents will be dying out in a few cycles or after few time. So such transients has to be eliminated, or you have to take the measurements only after the transient has died out. So if you are trying to measure it suddenly, once you are switching on the supply, you will be having transients coming into your measurement, which will be erroneous. And since you are using high voltages, the instruments which are used has to be protected from these high fields. So such arrangements also has to be made, or such instruments has to be used which can be used to measure high voltages as well as very low currents. So such protective arrangement also has to be made. Now coming to the guard circuit. The guard circuit is used to bypass the leakage current and or provide an alternate path for the leakage current. Now leakage current, once you are using such a circuit, you are trying to measure the insulation resistance. So we are splitting the insulation into two parts. One is the insulator as such and the equivalent resistance that is there. So once you have a leakage path available, whatever the current that is flowing through the ammeter, which is a micro ammeter which measures very low current, it will be composed of the current resistive going through the resistive portion of the insulator as well as the leakage current. Okay, leakage current through the section of the insulator. Now if you are providing a alternate path for the leakage current like this, we are bypassing the micro ammeter so that your leakage current is flowing like this. You are not eliminating the leakage current, but you are simply bypassing the leakage current from this ammeter. So that the ammeter will be reading only the current which is through the resistive part of the insulation. So you are having guard terminal. So you are connecting this guard terminal to the source, directly to the source, bypassing the micro ammeter, so that leakage current will be supplied from this point directly. Okay. In such a way you can eliminate the effect of leakage current. So in loss of charge method for measurement of high resistance, we have capacitor connected across the resistance which is to be measured. So capacitor is having a known value, and V is the electrostatic voltmeter which is used to measure the voltage across the capacitor, and R1 is the leakage resistance of the capacitor. So for a practical capacitor, this capacitor is associated with a leakage resistance. Okay, and ideally we say that the capacitor is having no resistance. Whatever the voltage to which it is charged, it will stay with the capacitor throughout the time period till the capacitor starts to discharge. So once the capacitor discharges, it will be having two paths. If it is discharging through R, it will be having two paths. One is the internal path which corresponds to the leakage resistance of the capacitor. Okay, so that simply means that if you are having some amount of energy associated with the capacitor, that energy won't be completely transferred to the resistor at which we are planning to discharge the capacitor. Some energy will be dissipated within the capacitor. So in order to represent that, we are representing that by means of a leakage resistance of the capacitor. So that is R1 is a total leakage resistance of the capacitor, and R is the resistance to be measured, which is of mega ohm range. Now the capacitor is of a known value. We connect the capacitor across the voltage source, and here we do it by the help of a switch which is known as a single pole double throw. So here pole means this is one pole, and you are able to switch it from position 1 and 2. Between 1 and 2 you are able to switch. So it is a single pole and you have double throw. You are able to throw it between 1 and 2 alternatively. So first we connect your switch to 1, and we have circuit like this. We have a battery through the capacitor. Okay, and we complete the circuit like this, and once the capacitor is connected like this, the capacitor will be charging to the supply voltage, and electrostatic voltmeter will be measuring that particular voltage. And once the capacitor is fully charged, or charged to some suitable voltage, a high voltage, now what happens? You will be putting the switch to the position number 2. Now once the switch is placed to position number 2, your circuit now becomes a continuous path like this, with resistance also in the circuit and voltmeter also connected, and your supply will be cut off. Now the capacitor acts as a DC source, and capacitor will be discharging to a parallel combination of R1 and R. So here your R1 and R are connected in parallel, and I am calling this parallel combination as R dash, which is R1 R by R1 plus R. Okay, so that is to simplify your analysis. Now what we do is that once the capacitor starts to discharge, we take the readings for a time period of T from the capacitor voltage reducing from V1 to V2. Okay, so you have initial voltage of V1 and it is reducing to V2 in time T. So during this time what happens? Okay, so at any instant, so this is already mentioned, R parallel R1 is taken as R dash. So at any instant t, voltage across the capacitor is V volts. Now your capacitor is connected like this. So this is R1 and this is R. So C is charged to some voltage. Now this capacitor can be thought of to be equivalent to a voltage source with a voltage V, which is connected across two resistors, R and R1 and R, or equivalent of R dash. Now at any instant t, V is the voltage across the capacitor, I is the current flowing, and Q is the coulomb or the charge associated with this particular capacitor Q. Now I can be written as minus dq by dt, since there is reduction in charge as the capacitor is discharging, which is equivalent to minus c dv by dt. Now I is also equivalent to V by R dash, where V is instantaneous voltage and R dash is the equivalent value of resistance. Now you can equate them together, so you will have V by R dash is equal to minus C dV by dt. So we rearrange the terms, dV by V is equal to minus dt by C into R dash. Now what we do is that since it is a continuous process, we integrate both the sides. The voltage is integrated from V1 to V2, since the voltage is reducing from V1 to V2, and the time from 0 to t. Now, so once we integrate this, what you will get is that log to the base e V1 by V2 is equal to minus t by R dash C, or V2 is equal to V1 e raised to minus t by RC. Now this can be represented like this. So this is T, and this is your instantaneous voltage V, and your voltage is reducing in an exponential form, and this voltage is V1. We start from V1, and at instant t, your voltage will be V2. So once the capacitor discharges from 0 to t, the voltage reduces from V1 to V2 in an exponential manner. So this is how you can represent the entire process. Now the value of R dash can be determined. How? Because here V2 is known, V1 is known, because we are measuring it using the electrostatic capacitor, electrostatic voltmeter, and C is also known. So the time is also being noted. Now the only unknown is R dash. Now the R dash can be determined from this equation. Now the test is repeated again by disconnecting this particular resistor R. R is the unknown resistor, and hence now the circuit has only R1, or only the capacitor with an internal leakage resistance of R1. Now you will get another equation, that is V2 dash equal to, you can think something like this, V1 dash into e raised to minus t dash by, this is R1 C. Okay, so here the only unknown is R1, so you can find out the value of R1 from this. So once R1 and R dash is obtained, now from the parallel combination equation we can easily find out the value of R, which is unknown. So R can be easily calculated from this calculation or this process. Okay, so this is how a high value of resistance, or in the mega ohm range of resistance, can be measured using loss of charge method. Why do you call this as a loss of charge? Because you have a capacitor which is charged to a particular voltage, and this capacitor is getting discharged to the resistor under test, and it is discharging in the sense it is capacitor is losing its charge to the resistor, and resistor consumes energy and it is dissipated in the form of heat. So whatever the charge is there, that is discharged into the resistor. So there is a loss of charge in the process. So it is known as a loss of charge method. So this is your capacitor C, okay, and discharged to the R, and practically this also will be having the leakage resistance R1. Okay, so this is how you find out the value of unknown resistance R. So thank you so much.